Hi, this is Sue Watkins. I'm the Climate Change Program Manager at the Institute for Tribal Environmental Professionals at Northern Arizona University. Thank you for joining the webinar. This webinar series is introducing the Local Environmental Observer Network, discussing extreme weather events, and discussing the impacts of climate change on human health and on fish and wildlife. We are offering the webinars with support from the U.S. Environmental Protection Agency. Oops. Darn. Today's webinar is going to focus on extreme weather events and climate change. This webinar is being recorded, and we will post the presentation and webinar recording on ITEP's Climate Change Webinars webpage. You can also download the presentation from the Handouts section on your GoToWebinar panel that should be on the right side of your screen. Please type any questions you have into the question box on the panel on the right side of your screen. And after the presentation, the presenter will answer questions. And following the webinar, you'll receive a link to a short online evaluation form. Please take a few minutes to provide feedback and suggestions for future webinars. Here is my contact information. ITEP's Climate Change Program offers climate change trainings, webinars, a tribal climate change newsletter, and the Tribes and Climate Change website, and much more. Please visit our program website at the URL listed on this slide, and please feel free to contact me if you have any questions about ITEP or our climate change program. I am very pleased to introduce Dr. Robert Rabin, who will be giving the presentation for this webinar. And at this time, we will switch over to his screen. Dr. Rabin has a BS and MS in meteorology from McGill University in Montreal, Canada, and a doctorate in meteorology from the Université Pierre et Marie Curie in Paris, France. His research interests include applications of satellite observations in thunderstorm research and in weather forecasting, the use of Doppler radar for measurement of winds and stability changes in the clear air prior to thunderstorm development, the effects of surface wetness and vegetation patterns on cumulus cloud formation, and medium and long-range weather forecasting of extreme weather. As I said, Dr. Rabin is a research meteorologist with the NOAA National Severe Storms Laboratory in Norman, Oklahoma, and he is working collaboratively with the NOAA NESDIS Applications Development Lab in Madison, Wisconsin, and the Regional and Mesoscale Meteorology Branch in Fort Collins, Colorado. The collaboration has led to several innovative research projects involving satellite measurements of mesoscale winds, surface wetness, and the monitoring convective storm clouds and trends in moisture and stability. Dr. Rabin also mentors students at the NOAA Cooperative Remote Sensing Science and Technology Center at the City College of New York and collaborates on GOESR satellite projects there. And he also serves on the board of directors of the Cultural Sharing Project. With that, I will turn it over to Dr. Rabin.
Thanks so much, Sue. I'm very pleased to be here. Welcome, everybody. Honored to be able to present this to you today. There, as you, I'm sure, are aware, many people, both in NOAA and universities and other countries, that have devoted much of their time to studying climate change and weather impacts on weather. What I'm going to emphasize today is extreme weather events, probably the most uncertain, perhaps controversial subject in climate change research. Most of the material that will be showing you, the highlighted findings, come from the IPCC report from 2013, climate change report called the Physical Science Basis. And there are also going to be other findings shown that I'll note as we go along. A lot of things to talk about. There's a lot of different types of extreme weather. I'll begin with extreme temperatures, hot and cold, hurricanes and tropical storms, extratropical storms, winter storms, droughts and floods, and then finally thunderstorms and tornadoes. So human effects on climate there's many reasons for that. The one we usually are most familiar with are the greenhouse gases, increased greenhouse gases emissions, also aerosols. But another effect that sometimes isn't so visible is effects of land surface changes due to urbanization, agricultural practices, things of that sort. One of the problems in trying to assess effects of humans on changes in climate is that there are just naturally large fluctuations in the weather and therefore in climate, and depending on what sort of time scales we're looking at, it varies to their intensity. One thing that is certain from the measurements we have is that the global surface air temperatures over both land and oceans have increased systematically over the last 100 years due to from the measurements we have. Another significant effect that's clearly been identified or measured is the increasing absorption of CO2 in the oceans and the effect of the chemistry of the water and effects on life in the ocean. So climate change, whether it's driven by natural or human forcing or a combination of both, can lead to changes in the possibility of occurrence of extreme weather events. This slide you're seeing shows the complex interactions in the atmosphere between the gases like ozone, greenhouse gases, clouds, aerosols, reflection off the Earth's surface and atmosphere. So there's many pathways to changes that can occur there. And then completing the circle, everything's a circle and things are interconnected in many ways, and each element's very important. Here, the Earth itself, the oceans, the ice and snow cover, the biomass over the land, people, everything interacts with everything else. And so that's what makes it very difficult to quantify sometimes a prediction of what's going to happen, because things adjust. There's so many natural pathways in this living system. Sure, everybody's seen graphs before of observed global temperature change. Here's one from the report. The various forecasts from climate models are shown in the right-hand part of there. I'll show you with my cursor here. The observed is from here to here. So the increases in temperature since 1950 globally have been roughly more than a half degree Celsius, plus or minus. And then since 2000, it looks like it's still going up, but not increasing as much as it was the previous decade. In terms of expected changes in extreme temperatures and precipitation from the climate models, this is an illustration of the shift here towards hotter temperatures, the solid curve being the forecast, climate forecast. It's just a schematic, the dashed line being what we have now. So the idea is that one could expect more extreme high temperatures and fewer extreme lower temperatures. In terms of day-to-day variability or variability from year to year in different scales, the models also seem to suggest that there'll be more variability in these extremes. So there'll still be cold extremes, many of them, but the absolute temperatures may not be quite as cold. And then finally, the precipitation, jumping down to this last panel here, change of the skewness, meaning that there'll be a redistribution of precipitation towards heavier events. The total precipitation may increase some, but the main impact on extreme events, such that could affect flooding, for example, is that more of the rain will be partitioned into heavier, more extreme events. So I'm going to move on to hurricanes and tropical storms. These bullets are findings from the report, IPCC report I indicated earlier. I want to emphasize that there's some uncertainty in whether the number of tropical cyclones will change much, but what seems more probable is that that the maximum wind speeds and precipitation rates might be higher in more of the cyclones. One problem, again, in pinpointing details, making forecasts because of the limitations in our ability to forecast, is that that the effect of climate change on the tropical cyclones is likely to vary depending on what part of the world you're in. So there's low confidence in specifically saying there'll be more hurricanes, say, in the Gulf of Mexico or the Western Pacific, as opposed to a global change. Unfortunately, we just don't have the confidence to do that yet. There's medium confidence the precipitation will be more extreme near the centers of tropical cyclones when they make landfall in northern and Central America. So that has a big impact on extreme precipitation amounts along the coastlines. And then finally, the frequency of intense storms, more likely than not, will increase in some basins, but again, it's hard to say which ones. So this is a map that shows, it's a plot of all the major hurricanes since 1851 around North America. The yellow curves would be tracks of major hurricanes. The red would be tropical storms, so they haven't reached hurricane intensity. So for example, coming off the west coast of Africa here, they move westward towards the Caribbean, and they're not hurricanes yet often. There's also another track that you see of hurricane development off of central Mexico. Those move northwestward, going towards the central Pacific, but occasionally they stay off the coast, but occasionally you'll see some tracks here where they will affect western Mexico, and then moving inland, so hard to see. Sometimes the remnants of these storms move into the desert Southwest. I'll be talking about that more later. And then these little red curves here indicate that many of these storms, although they weaken in terms of wind intensity, still pose problems when they enter the continent with heavy flooding. So what's the observed trend in these storms? This plot gives an indication of the trend of the amounts. So this goes back to 1855. The red bars are the number of hurricanes with Category 3 or greater. 5 is the highest. So you can see that there are periods of times, like decadal periods, like from 1945 to 1965, there seemed to be higher amounts of these stronger hurricanes, and they decreased again for a number of years, and increased again in the 90s. The yellow are just named storms. They include everything, whether they're a hurricane or not, and then the green would be all hurricanes. So depending on how you look at that, it's not an extremely convincing or strong signal that there's a systematic change happening in hurricane numbers yet of various intensities affecting the U.S. area. That's just what we have to go by in terms of observations. In terms of the climate models, this shows a forecast over the next century or so of changes in of hurricane numbers and intensities by hurricane basins. So we're going to concentrate on the North Atlantic one, which is this upper right one here. And it's a little hard to see. I know it's small, but this number 2 second bar graph shows what is expected in terms of strong hurricanes, Category 4 and 5, their frequency. So the models seem to still give some indication that there's going to be a significant upward trend in the storms in the North Atlantic in terms of strong frequency of these strong hurricanes. That's not true in some of the other ocean basins. So that's just what we have to go by from the forecast now. Now I wanted to mention something about sea level rise because it's a combination of the sea level rise if it occurs with the winds, the storm surges due to the strong winds from tropical storms as they make landfall that can really inundate areas, at least temporarily, and cause extreme problems. So the observed sea level rise since 1950, shown from here to here, from various types of measurements. You can see it's on the order of roughly 5 centimeters or so. So not extreme yet. And then since 1990, it's gone up at a higher rate. So right now we've increased something like 15 centimeters roughly, which would be 6 inches, something like that. And then depending on the different forecasts available from different climate models, there's a large variation going out to the year 2030. But if we take the worst case scenario, that's a more significant rise, obviously. And so the impact of a similar strength storm in 1930 will be a lot more than it is now due to higher sea level. So I'm going to move on now to extratropical storms. Those are just storms that are outside of the tropics. They're typical low pressure systems, wintertime storms, and other times of the year that have large scale winds and precipitation with them. They provide most of the precipitation over most of the world during the course of the year. The models, to sum up what you're seeing there, the models suggest that there more likely than not will be shifts in the storm tracks due to the heating in the Arctic. The jet streams will move northward. So primarily affecting Alaska and coastal Canada, as the North Pacific storm track will likely shift a little bit, somewhat more poleward, which will change the precipitation patterns in Alaska. Also, the amount of precipitation is likely to increase in the Arctic and overall in North America. That's the projection. Also, the other thing, which I'll be talking about more, is a shift towards more extreme, more of the precipitation that's falling will be in the extreme categories. The totals go up, but the number of extremely heavy frequencies go up even more. This gives you some better picture of the current storm track. So this is North America here. We're looking at pretty much the whole world on this little box here. And the black arrows show kind of a typical storm track from near Japan to, say, the coast of British Columbia. And there's another major storm track from the northeast coast of the U.S. up to Scandinavia. And they vary a lot. They vary. They're never this perfect. Storm tracks are dip and go up, but this is just a schematic shows the overall. So the idea is that likely due to more warming in the Arctic, this will move up and reach the coast further north. This is Alaska up here. So that's what I wanted to show from that schematic. In terms of the total amount of annual precipitation or precipitation by month, um, the maps here show this. The upper three are the summer months, and the lower three are the winter months. This over the next 100 years, I believe, and so it's expected or predicted precipitation amounts for those summer and winter seasons. The blue being increases, the reds being decreases. So you can see, and these are three different climate models in the columns. So that's one climate model, that's another, and that's another. They're all a little bit different, but to some degree they're showing a tendency for, in the summer months, more precipitation in the southeast U.S. and then somewhat drier in the parts of the plains and Pacific Northwest. But it varies from model to model. So there's still quite a bit of uncertainty in the locations of these changes, and they don't really reflect the extreme events necessarily. They're just averages over a long period of time. So I want to touch on or concentrate more of my time on a specific phenomena that's of importance to the desert Southwest states and northern Mexico. It's called the Southwest monsoon. Some of you may know quite a bit about this, especially if you live in that part of the area. Monsoons, we typically think of the monsoon in India. Monsoon in general is just a persistent change in the wind flow pattern, but often it will affect precipitation, heavy precipitation. I'll be showing you some maps here in a minute. Parts of the desert Southwest, it's very critical, the amount of precipitation that comes out of the monsoons in the summertime, because they make up a significant amount of the precipitation for the year, and when that arrives is also important. So the climate models, this is a summary of what the climate models predict. These are the observations based on studies of what's known about changes in the monsoon precipitation. There's been no distinct trends in the annual precipitation from the monsoon in the last 50 years, but bullet number 3 is important. There has been, the observations have shown that these events have been increasing in intensity, precipitation intensity, but they're less frequent. So the total precipitation may be the same, but they're coming in more intense bursts, which again have an implication towards flash flooding and also water getting into the ground. And then the length of the monsoon season itself, there's evidence that that's been decreasing. The next bullet here mentions that there's also been a delay in the beginning of the monsoon. So you'll see later it's a summer phenomena. So the later it comes in, the hotter, more dry the conditions will be before the onset. Related to what I was talking about, hurricanes making landfall, has been observed. There have been more cases recently of extreme precipitation occurring with landfilling hurricanes. We actually had an event here in Oklahoma just about a week ago of a situation like that that produced up to 8 inches of rain in south central Oklahoma. You may have heard of that, in North Texas. And then the other thing is there's a trend that the area affected by the monsoon has become further north. So the core area, which is mostly Arizona and western New Mexico, seems to be shifting further north. Forecasts for this based on climate models. Unfortunately, the models don't seem to be capable yet of modeling this well, so the forecasts are probably very questionable. So very low confidence in how the monsoon precipitation may change at this point due to larger scale climate changes. One thing, though, that is more certain is that since the increased temperature that is expected due to climate change, that will lead to higher summer temperatures, extreme temperatures before the onset of the monsoon in the desert Southwest, and then there'll be more consecutive dry days, more risk of wildfires, and shortages of precipitation. What I'm going to show you now is based on a couple things. Excuse me. One was a report to the nation called Our Changing Planet from NOAA on the monsoon, and the other is from this published study by Adams and Comrie. So this is the general region. I'm sure you're very familiar with it. The Southwest U.S., but also going further north into almost the Pacific Northwest, Rocky Mountain, the Intermountain region, and then Mexico. The monsoon, the formation of these precipitation events, they're convective, meaning thunderstorms in nature. This is a cross section, the eastern Pacific to the west, Gulf of Mexico, and then there's the Gulf of California, which is this narrow area of sea between Baja California and mainland Mexico. So typically what happens is the storms form over the mountains like they do in the Rockies. In the middle part of the day, there's sinking motion on the sides, and it sets up a large-scale pattern, and these storms continue to grow and expand in the course of the afternoon and then peak at night. This map shows the distribution of precipitation at various locations. So this is Tucson, this is southern New Mexico, Las Vegas, Grand Junction, California, Grand Junction, Colorado, to give you an idea. And these bar graphs, which are small, show the average precipitation by month. So what you're seeing, for example, at Tucson is there's a peak of precipitation in the summer months, not so much in the winter months. That's similar to southern New Mexico and many places in northern Mexico. When you get further north into places like the mountains in Utah, Colorado, the precipitation is more even through the year. So what I'm emphasizing here is the importance of this particular monsoon pattern plays a very large role in the annual precipitation in the desert Southwest area, particularly southern New Mexico and southern Arizona, but sometimes these patterns extend further north. Another attribute of the rains or precipitation from the monsoon, this is a map of Arizona. In the desert areas of the southern parts of the state in particular, a lot of the precipitation actually falls after dark. It's more of a nocturnal event, whereas in the mountains, it's more during the peak of the day, typically in mountain areas. So this also has an impact on the weather, extreme weather in these regions, because it may still get very hot with fewer clouds during the afternoons, and then the storms come at night. They're not really helping in terms of modifying the air during the day. This is to give you a better picture, the tropical connection of moisture getting into the deserts actually comes up from sometimes some of these tropical storms coming off of Mexico. This is the western Mexico coast here. Some of the moisture will split off and come up through the Gulf of California and then in through the valleys into southwest Arizona, and then make their way up further north. And then that interacts with troughs or upper air disturbances further north coming across. So it's fairly complex, but there's a connection in the atmosphere between all the airflows. So when do the rains actually commence typically over these areas? This map from the Wildland Fire Predictive Services shows average startup dates. So the red curves would be early July. Blue out here is June. So usually not much rainfall out here till mid-July, and then as you go further west, late July. And again, the climate models seem to indicate that this may tend to be delayed further into the year, although it's fairly uncertain. The patterns of precipitation is influenced. The monsoon patterns are greatly influenced not only by what's happening in the tropics, but the jet stream pattern further north in the summertime as it shifts north. So up here, this is a typical wet pattern when you have a ridge aloft or a high pressure aloft in the northern plains that allows more of a southerly flow to the west of it, versus when you get a pattern like it's setting up this week where you have more of a ridge in the west, a trough over the Great Lakes, and then you have more of a dry flow over the area. So these patterns sometimes are persistent for weeks at a time. Sometimes they're predominant for one whole season or several seasons in a row. Sometimes they fluctuate very often over from day to day almost. It just varies a lot. What are the related phenomena and risks associated with the monsoon flow? Well, it provides very beneficial rainfall, obviously, to the dry areas, but it also has certain hazards, and so these hazards may become more predominant if there's changes in the future in the frequency of these events. So this is a satellite image of southern Arizona, and in the early afternoon, there's already some cloud development, convective cloud development over the higher terrain. And then as we approach late afternoon, it expands. You have the most violent parts of the storm down still here, but now it's really expanded. So that's kind of a typical pattern that you'll see. It starts around midday, very localized, and then gets big by late afternoon and evening. This is just a cloud top temperature image. And this is a radar picture for the same area. So the red areas are the intense, very intense downpours, probably lots of lightning. And if they don't move much for several hours, flash flooding becomes imminent. So here's a picture of a cloud, one of these growing cumulus clouds taken from an aircraft, I believe. And one of the things that often happen in the west, in the mountainous areas in the west, where the desert southwest or further north and in Alaska, is wildfires. Especially if it's been dry, like it would be before the monsoon comes, you have forest fires starting. The smoke from those forest fires can actually, in some sense, ignite thunderstorms or start thunderstorms forming. And so what you're looking at there is actually the water vapor, the clouds. They're made out of water. They're not smoke anymore. And what I'm going to show you next is a YouTube video of, let's see if it comes up here, of what this looks like from a camera. Hopefully it will come up here in a minute. So these thunderstorms, one of the interesting things about them, since they're initiated by smoke and heat, there it is. So this is a fire, the King Fire in California. It's not animated. It's going to take a little while there. Not playing very. There we go. A little bit better anyway. Having some internet issues here, I'm afraid. Go back here so I can start it again. Give it one more try. Oh, so what I wanted to mention additionally is that these storms can actually, because there's strong updrafts in them, they can literally carry the smoke from fires into the stratosphere. Once they're in the stratosphere, just like volcanic ash, they get distributed. They can go all the way around the globe, and because they go all the way around the globe, they will cause they can cause long-lasting effects in the stratosphere. So I'm going to move on here because this is not working very well at the moment. The other thing that that I'm sure people that are join in here who live in the desert Southwest are familiar with are haboobs. Haboob is a dust cloud that it's actually from Arabic. Got one of those there. We're having some internet issues. I'm sorry about that, but we'll see what happens. These dust clouds, if this ever comes up, these dust clouds are, there we go, caused by outflow, sometimes a dry outflow from the thunderstorms. They pick up huge amounts of upper soil dust from the ground and then move it long distances. They're a hazard because of the lower visibility. I'm sorry, this is just not playing very well at the moment, but you can look at this later on the when the talk is posted again, if you like. So I'm going to move on here because of limited time. The next slide here shows another map where we have our monsoon flow, which I showed you earlier, coming up the Gulf of California. But at the same time, it's common to get moisture coming up from the Gulf of Mexico on the other side of the Rockies and moving up into the foothills of Colorado, New Mexico, Wyoming, and Montana. So let's move on here. I'm sorry, I am having some computer issues at the moment. Bear with me. Try to shut some of these screens, and maybe that will help. I don't know. Let's see. Okay. Hopefully I'll get my screen back here. There we go. So let me just go back to full screen. Okay, so these intrusions of moisture can cause severe flooding. Here's a picture from flood that occurred in September of 2013 in the Boulder Fort Collins area. And what I want to show you now was an analysis of whether the frequency of intense precipitation has been changing. And it has, according to the analysis of data going back to 1910. So what you're looking at here are individual areas of the country, and when you see the bar graphs towards the right of each of these graphs, that's showing that more of the annual precipitation is coming in heavier bursts of precipitation rather than lighter precipitation if it would be on the left side. This shows a national trend in increasing amounts of intense precipitation. So not necessarily increasing the annual precipitation at any locations, but the percent of the precipitation coming in more intense amounts, shorter time frames. There's a trend, upward trend has been observed in that. Also, precipitation and damaging floods. I wanted to mention that from this study that the relationship of not only climate change, but the way the water interacts with the ground when flooding occurs, and then societal changes, they all are players, are important, play important roles in damaging floods. And how they all interact is very, very complicated. So the main point is that climate change does play an important role in determining flood damage, but by no means is it the only variable. There's many others as well. The good news is that planning for floods can really make a difference in terms of decreasing their severity. This is a flow chart. Again, it's too small to read the individual things, but it shows that contributing factors of floods are, one, the amount of water coming, weather intensifying conditions, land use, air pollution may be one that could affect it, pre-existing conditions, how wet the soil's been or dry, and then human impact, retainment, more pavements, parking lots, things like that come into play. And then over in the third column, we have policy. So to mitigate floods, there's various things. Of course, after a flood happens, disaster assistance, but then structural mitigation is another one. And then the other was floodplain occupancy. There's more people living in floodplains now, so there's more people at risk. So that's exposure. These two plots show trends in flood damage. It's in dollars, but it's been normalized to $1995, and it's also been normalized per capita. So you can see there's a lot of variability from year to year in terms of flood damage. Slight upward trend since 1930s to 2000 in this plot, but then if we normalize by the unit wealth, it actually has gone down. So we're talking about damage in terms of property values, or it's affected by generally the population being more wealthy, not everybody, of course, but often building of condominiums along the Gulf Coast or Southeast Coast is an example of that. I want to talk about drought now. So one thing, this report comes from the National Climate Center. The timing and evolution of droughts in the areas impacted are extremely variable, and so it's very difficult to understand exactly what causes drought onset and how persistent it will be. The Central High Plains appears to be the region most affected by the most persistent droughts. The Southern Plains, parts of Texas, Oklahoma, appear to suffer from the highest frequency of drought. But the other thing is droughts can occur just about any place. Sometimes we may lose sight of that. So these show some examples of droughts that lasted at least a couple years, each of them. So 1992, Northern California, Pacific Northwest, Northeast U.S., in 65. The Great Drought in the southern parts of the southern plains, high plains in '53 that affected our area here in Oklahoma. And then in the '30s, the Great Dust Bowl drought. American drought. This is another look at it from a perspective by Cook and Kane, and they went back and tried to reconstruct past droughts over North America. This shows the locations of some more recent droughts in the 2002 region in the Southwest, the Northern Plains in 1980 and 1988. These are based on a measure called the Palmer Drought Severity Index, PDSI, sorry. So it tries to quantify droughts by soil moisture. There's various uncertainties in that, and there's various ways to define drought, but that's just one of them. And these are two of the greater drought, the most severe droughts known in the 1900s. The Dust Bowl drought, 1934, affected a huge part of the country, and then '56 with this more localized drought in the southern and central plains. But then going back from the tree ring analysis into the 1300s, and these are just estimates and not completely certain, of course. You can see that there were droughts, decadal droughts that occurred various times in that century, and then in the 14 and 1500s. Another thing that is interesting to consider is that some of the areas that are typically affected by drought occasionally get excessive precipitation. So here's an example of the desert Southwest from 1867 to '69, this 2-year period, having excessive precipitation, where just a few decades earlier it was under severe drought. So sometimes that has led in history to a misnotion of people moving into these areas thinking that is the climate of the area, and they start up agriculture and then it all dies off. Another example of that here in Oklahoma is the annual recorded precipitation. I'm just going to back out of this for a minute. Okay. Make sure everybody's still here. Okay, so back here again. So this is a plot of annual precipitation from 1900 to 2015 here in central Oklahoma. You can see just how variable it is from year to year. Sometimes you have successive years, dry and wet. So if you were to have grown up here in the 1980s and 1990s, by the year 2000, your view of how much precipitation falls here would have been about 40 inches. And then what happened? We had the drought years after 2000, at least some of the years where the precipitation dropped below 30 inches. Was not uncommon if you look back at the earlier years, but it can be so variable that one can, if they don't have a long history from their ancestors or their elders, they may get a misconception of what the climate is actually like over a long period of time. So this year, 2015, we had 23 inches of rain in the month of May alone, just following several years of drought. Our annual average is only 33 inches, and then we've had 7 years in following year. So finally, I want to talk about tornado occurrence. We have tornadoes are a risk mostly in the central U.S. and they can affect almost any part of the U.S., particularly the central and eastern U.S., but they're most frequent in the central U.S., the southeast states, in the in the early spring, particularly, and they migrate north. So it's a picture of a massive tornado. And these results are based on the study that I just showed you the slide from by Brooks and others. What they found was they were looking at trends of tornadoes. We don't have a long record of tornadoes, and there's some problems in those records because of changes in the method of observations and the accessibility to observing tornadoes. But what they found was that there was no major trend in tornadoes over the period of time since the record started. But it looked like they're more variable since the 70s. Less tornadoes less days of tornadoes per year, but more days with tornado outbreaks or many tornadoes. Why this is uncertain, but that's appears to be the trend. And then the other item of note is that the timing of the start of the tornado season seems to have gotten earlier, which may have something to do with a warmer climate. So here's a plot that shows the number of tornadoes since 1955. It's been normalized to try to take into account changes in the way the observations have been done. And you can see it would be difficult to say the trend overall has been upward or downward, although there are decadal time length changes in that. And then this plot shows that the upper plot is the number of days per year with at least one tornado reported, and you see that there's been a downward trend in that from 1960 to 2010. Whereas the lower curve is the number of days with more than 30 tornadoes, and that's gone up. So that's the graph that backs up the results, showing that there's been a trend to a change in the way the number of tornadoes per day, but fewer days with tornadoes. The summary of the tornado research on changes in tornadoes and projections towards the future with climate change are shown on this slide. The instability due to the additional heat and moisture in the atmosphere, which is attending the global warming, is projected to increase over the U.S. Over the next century. That could lead to more extreme, intense rainfall, thunderstorms. However, there's also a projection that the wind shear will decrease, and that's because the jet stream becoming somewhat weaker, migrating further north as the poles warm. Tornadoes require both instability and wind shear, so the net effect is that the frequency of severe thunderstorms may increase to some extent because of more moisture and heat, but the fraction of those storms that produce tornadoes may actually decrease because of the reduced shear. But scientists are not very confident in predicting changes in mean tornado frequency or occurrence with global warming. I want to leave you, before I get to the final conclusions, hopefully this will come up here, I wanted to leave you with a little story along the north slope of Alaska. So this is our slope here, this is Barrow here. This is a animation from the geostationary weather satellite GOES from a couple years ago, June 14th, 2013. And that time of the year, it's light 24 hours a day up in at this latitude. You can see the ice cover if you look closely here. I'll try to speed this up. It's hard to see, but there's ice cover. There's water here, ice cover here. That's the coast. But these are clouds, and some of these are actually thunderstorms. And so the temperature in Barrow actually got up in the upper 60s that day. Typically, it stays in the 30s. Most of the summer can get up into the 50s occasionally, but this was an extraordinary day. And so there was a thunderstorm in Barrow, and many of the people I talked to had never seen a thunderstorm in their life. They went up to the tops of the bank building and other places to actually, they heard thunder and to look at the clouds because it was something that had never occurred before during their lifetime. So that was phenomenal. And with the projections of the jet stream moving north, if the Arctic continues to warm as it has been, influx of these potentially warm, moist air from southern latitudes making it up to the Arctic may become more common. There was actually another day the same year. There were 2 days, or maybe it was the year before, that had thunderstorms. I don't know. I don't think they've had them since, but I wanted to show you that. So in conclusion, I am going to go to the summary of the talk. The takeaway points is that there's evidence it's been happening due to the measurements we have, backed up by the measurements we have and projected by climate models, that more extreme precipitation events will be in the offing, both from hurricanes making landfall and just from inland thunderstorms, which will lead to more flash flooding issues. In terms of flood impacts from flash flooding, there are additional effects besides changes in the frequency of extreme heavy rain, which have as important or more important consequences, and some of those things we can change through better planning. Possible shift in large-scale storm tracks will certainly have large impacts on vegetation cover, agriculture, some areas becoming drier, some becoming wetter. The monsoon specific to the southwest U.S., we don't have, there's not much confidence in how well that can be forecast at this time. However, there's some indications from observations that the annual onset has been delayed and that it extends further northward, which would give more precipitation further north. A variety of phenomena can occur as a result of monsoon-related phenomena. Extreme wind events from dry thunderstorms, which can fuel fires from lightning or other startups, can also lead to extreme blowing dust conditions, which can obscure visibility and also disrupt the ecosystem. And then probably a more prolonged period prone to fires before the rains actually set in, and then more intense floods perhaps with the monsoon storms. Droughts, still somewhat of an uncertainty in forecasting what will happen, if any significant changes will happen. We know that droughts have been with us. They last sometimes for decades and sometimes shorter periods, and they can occur almost in any region, although still the plains, central and southern plains, seem to be the most frequent target for droughts. And then finally, the local action can have a significant effect on the hazard mitigation. So we're facing things that have happened in the past, perhaps with more frequency and changing where they're happening. So it's important to plan for those, prepare, and then be able to execute those plans. So I'll stop there. I went over a little bit of time, and hopefully everybody is still here.
Yeah, thank you, Bob. We do have a few questions that have been typed in during your presentation, and if anyone has questions and they haven't typed them in, please do so now. The first question was from early on in your talk, I think referring to your slide about sea level rise. And they just had a question, what does FAR, SAR, and TAR stand for? I think
very good question.
maybe the climate models are, is my guess, but I'm sure you...
Let's see if I can get back to that slide.
It was near the beginning of your talk.
Yeah. Unfortunately, my computer slowed down, and it's moving rather slowly, but it's moving here, so just bear with me for a second. I can tell you what SAR means. It's a synthetic aperture radar. So for about 10, 20 years ago, the only way to measure sea level was with gauges, actually, physical measurements of the at specific locations like harbors. And that's what's referred this. I don't know if you can see the slide now, but the upper three colors or curves. Is this the right slide?
I believe so.
Okay. Okay. But the question, I guess, is going into here, not that. Okay. Yeah. So to be honest, I am not 100% what these are. They are different models, but I don't know offhand what those acronyms. I'm sorry. I did want to point out though that I was referring to something else because SAR is a synthetic aperture radar, and so since the last 20 years or so, there's a capability to measure sea surface very accurately through altimeters from satellite over large areas of the ocean. So our accuracy of measurements of sea level have improved greatly in the last 20 years or so. But I'm sorry, I don't know the specific answer to those groups of models.
Okay, the next question was when you were talking about pyrocumulus clouds. So the question is, so when a pyrocumulus cloud reaches the stratosphere, you said it can have long-lasting effects. What sort of effects can it have?
Okay. It's known that volcanoes can cause cooling, global cooling that can last for, say, 2 or 3 years. And the reason is that there's an injection of aerosols from the volcanic ash that goes into the stratosphere. Once it gets into the stratosphere, it stays there for a long time, stable. It doesn't fall out, and it gets carried by winds, and so that debris or that ash is circulated around the globe basically and gets distributed over a long area. And the net effect of it is to reflect more sunlight away, so there's a net cooling effect. It's been hypothesized that pyrocumulus may play a similar role, but maybe not as strong because there's ash from the fires. The ash will be a different chemical composition than it would be from a volcano, though. Wouldn't necessarily have sulfur in it, but it could also get into the stratosphere, and once it's in the stratosphere, it just stays there for at least a couple years, and that's what I meant by long-lasting. Not 100 years, but a couple years.
Okay, and then when you were trying to show the Haboob video, someone wrote that they Googled the name of the Haboob dust storm in Arizona, and they were able to find it and watch it. And they just said your presentation was very informative.
Well, great. Yeah, I'm sorry that it didn't play quite right. I think I'm just having some technical issues with my computer.
Okay, and then another question. Has there been any plotting of the tornado track? From a layperson, it seems to have moved from Texas, Oklahoma, Kansas to the east.
Oh, that's an excellent question. I'm glad whoever asked that. Overall, yes, there are, and if you're interested, get in contact with me. There are some references I can give you with that documentation on that. there have been many studies done on the tracks and the frequency of tornadoes. There's no evidence that it has shifted, however. The peak frequency of tornadoes in May is still bullseye right over Oklahoma and Kansas. There are historical events of tornadoes, and I know why this perception is there, because they happen fairly rarely, but there are major tornado outbreaks that cover large areas that tend to be more in the Ohio Valley and further east. So I'll give you an example. There was the so-called super tornado outbreak of April 3rd and 4th, 1974. Those 2 days had the most tornadoes that ever occurred in recent history, for any one tornado outbreak. The peak of that was in Ohio. Okay, Xenia, Ohio was a small town that had an F5 tornado that was completely wiped out. But there were, I believe, over 100 tornadoes. I'd have to look it up. So that was in 1974. You can go back further. In 1953, there was an F5 tornado that hit Worcester, Massachusetts. So historically, and it's a short period because our recorded history of tornadoes is relatively short. It goes back maybe to the 1910 or so, and there weren't as many people around to observe them. But we have had these large tornado outbreaks to the east. Even the tri-state tornado around 1923, I think it was, went from eastern Missouri through Illinois and Indiana. But that's a great thing to wonder about.
Okay, someone wrote in just some information about the FAR, SAR, and TAR, and it said that that's referring to the first, second, and third assessment reports, and it's the range of sea level rise projections from each of those reports.
Oh, great.
So thank you for writing that in. And there aren't any other questions, but I have one for you. And while I'm asking the question, if anyone else has any questions, please type them in right now. So I was just wondering, are there any predictions for the jet stream shifting because of climate change?
There are many predictions. That's also a really good thing to think about and wonder about. I haven't seen a consensus of opinions on it. Certainly in a gross sense, the projection is that the jet stream will tend to be further north, just simply because of the Arctic warming more than the lower latitudes. And essentially that means the upper winds will be somewhat weaker in the mid-latitudes where most of the continental U.S. lies, and the flow being weaker, things won't move as quick, storms won't move in and out as quickly, large-scale storms. So I would say that's the basic understanding, prediction there. I can say from what I've read and studied is that there is no evidence from the data we have yet now to indicate that there has been any systematic shift. I know there were a lot of articles in the paper and in the media about the polar vortex in the last couple winters, shifting south, and mentioned that some of that may be related to slower jet stream, but there doesn't seem to be any real firm observational evidence that there's been any systematic change. And one thing I did not include in the report, I thought it was a bit too technical, was something called blocking. Well, block is simple to understand. It's when the upper flow becomes blocked, and then the patterns don't shift anymore for a while. And blocks are a normal pattern that will set up from time to time, and so we were in one last month where we had those excessive rains here. Another part of the country may have been very dry. Things were just not progressing through. And so the IPCC report indicates that based on the climate models are run, there was no evidence that blocks would become more frequent. So that was this kind of maybe counter in a way to the idea of the flow slowing down. But I think that it's still a little uncertain what will happen there. But all I can say is that there's not enough evidence yet to say that it's been observed to have been shifting.
Okay. There's another question. Actually, I'm glad you have the slide up on sea level rise because it's referring to that. Do those sea level rise projections take into consideration the collapse of the Antarctic ice shelf?
Oh, the predictions?
Yeah, if it melted.
Right. Unfortunately, I'm not, I wasn't really going to talk so much about the technical issues of sea rise. My understanding, and I would like people to verify this on their own too. My understanding is that the models that this is based on do include, or try to include, changes in the ice sheets. In other words, if there's warming, the melting. I think there's a lot of uncertainty in those. I think you see that in the different slopes there. So I guess the question is, to what extent is that well modeled is also another question. But I could be wrong. I don't want to answer that in a completely affirmative way because I haven't actually gone and looked at that in detail. But my speculation is yes. And there has been some evidence, you may have read about this too, that there's a bipolar effect between the southern pole, the north pole and the south pole, Antarctic and the Arctic, and that the overall there's been some increase in ice cover in the Antarctic, while the Arctic ice cover has definitely been going down. There are exceptions to that locally, of course, but overall, that's my understanding. I hope that answers the question.
Okay, thanks. And someone typed in the chat box, which probably everyone could see, that the Colville Reservation experienced a haboob in 2014, and the Colville Reservation is in the state of Washington.
Oh, wow.
So, yeah, north central Washington. So, and I remember hearing about that as well. Someone typed in a question, has cloud seeding added to climate change? If so, any indication that people will discontinue this practice?
Yeah, that's a very good question. Fresh my answer could be too long, but I'll try to keep it short. In the scientific community, at least in the atmospheric scientific community, there's an overwhelming consensus. Of course, there are some exceptions to it. The cloud seeding has no effect on precipitation in a large way. It's been a practice, of course, you may know, that goes back to, I don't know, the 1940s at least. And it may have some very small effects, but what I would mention is that there is a lot of research that has shown effects, unintended cloud seeding from aerosols from burning, biomass burning, whether it's from agricultural fires or from cities, from exhaust, diesel exhaust. That those aerosols can affect the efficiency of precipitation in clouds, and then be in some sense a type of unintended cloud seeding. So I would think that is something that would be a more pressing issue, or more, not pressing issue, but more dominant than man-made cloud seeding. I I don't think there's much evidence that the man-made cloud seeding has much of an effect either way. Could have a small effect, but I hope that answers the question.
Okay, thank you. Any last questions from anyone? Type it in now. Here's your last chance. And while we wait another minute or so, I want to remind people that we are going to have another webinar on Monday at the same time, featuring Kurt Johnson, who is the National Climate Change Scientist for the U.S. Fish and Wildlife Service, and he'll be talking about climate change impacts on fish and wildlife. So if you want to join the webinar and haven't registered yet, please do so. Let's see. I do not see any more questions. Let me just check. So I guess with that, we will end the webinar. Bob, thank you again for joining the webinar and giving your presentation. And I'm sure if anyone has any questions, they can contact you and ask their question to you individually. Someone just asked me about the webinar on Monday, and is it 10 a.m. Alaska time? Yes, 10 a.m. Alaska, 11 Pacific, 12 Mountain, 1 Central, and 2 Eastern. Hopefully I got that right. So anyway, thanks again, Bob. We appreciate you taking the time, and everyone else, thanks for joining, and hope to have you on the webinar on Monday. Okay, thank you. Bye.
Thanks for having me.